Hello, this is Bryant Myers, and welcome to another episode of Debunking Flat Earth. This is review part 2 of my debate with Austin Witsit, and in this video we're going to kind of continue a little bit from the last one where we talked about how uniform and how constant the Earth's gravitational field is. Now we're going to contrast that to how non-constant the electric field of the Earth is, and this is kind of maybe a multiple part series of the catastrophic failures of incoherent dielectric acceleration or any attempts to use electrostatics to describe gravity. So I want to start with a little soundbite from Austin, and then just like last time, I'll come back in and then we'll talk about it.
What we actually see is that we have atmospheric electricity on the Earth. So we have an increase, equipotential increase. It goes up 100 volts per meter. Okay? So there's positive charge, potential charge increasing up from the surface, 100 volts per meter. Now, the only way that that can be replicated or accomplished in any way, in any actual demonstration in the world, is you have to have two Gaussian surfaces. You have to have a surface above and a surface below to get that equipotential increase. It's the only way. There's no other way that can be demonstrated. Well, we have that on the Earth. We have equipotential increase, which means there has to be a surface above us acting as the second Gaussian surface, and that's what gives you this downward flow of electricity on the Earth. So that's what gives you the downward bias.
Okay, so we heard Austin talk about the two Gaussian surfaces creating the 100 volt per meter of voltage increase as you go up the atmosphere. And we'll see that that's not exactly true. And I first want to just address one thing, because he said it's the only way. So I did a little calculation. Actually, you can create with an infinite plane at just one Gaussian surface, you can create a static 100 volt per meter electric field if your current density is 1.77 times 10 to the minus 9th coulombs per meter squared. And I just had a little fun doing the calculations here. It's always fun when you don't have to do integrals because the area is a constant here on an infinite plane. But just basically from kind of basic electrostatics, you can easily use Gauss's law to calculate what the electric field would be. And so I just wanted to say this because he said it's the only way, and it's not the only way. You can do it with one Gaussian surface. And I didn't get this until after the debate. The reason he was saying two Gaussian surfaces was that I guess, and I got this from another one of his recordings, is that the other top Gaussian surface is the dome, when in reality, on Earth, I mean, yes, there are two relatively, you could call them Gaussian surfaces. I like to think of it more as a parallel plate capacitor, just as far as just a more concrete way of visualizing it. And, basically the ground is one part of the capacitor, and the upper layer of the atmosphere, about 50 kilometers up, is the top part, and you got positive charge on the bottom layer, or this upper atmosphere, and negative charge on the Earth. So just to kind of recap from the last video, we talked about how the Earth's gravitational acceleration at the surface is relatively constant. It varies by around 9.76, 9.77, up to 9.83. And this does account, as I said in the last video, for all the gravitational anomalies. It certainly accounts for even if there's rain or other gravitational waves from the weather. It's those little small changes aren't enough. They're just very small, as I talked about in the last video. So we kind of went through this in the last video. I did email Austin, and I did get a response. So I'm glad he responded to this. So I'm just going to show the part about the weather and the gravitational anomalies, because he did respond to that. So here's his response here at the top. So he says, none of that matters though. Gravity cannot explain any change because of thunderstorms, rain, and wind. How small it is does not matter, and the fact that it stays within that range does not in any way rebut my claim about it being electrostatic acceleration. So remember, I talked about yesterday that gravitational acceleration only varied by about 0.7%. Very, very small percentage. So we're going to see, I underlined this in red here, because his claim that this does not rebut his claim about it being electrostatic acceleration, I'm going to demolish that in this video because it certainly does rebut it. And we're going to see why. So the first thing I want to talk about is the well-known Carnegie curve. This was an incredibly meticulous study done in the earlier 1900s, And it basically showed, without getting into all the details of the study, you can see the link here, you can look it up yourself. It basically showed that across the Earth, the global electric field changes by time of day. And see, where I underlined in red, it changes by up to 15%. Okay, so remember, 0.7% was what the gravitational acceleration was changing by. But now we have here proof. In fact, this is so well known, this Carnegie curve, that it is considered a law. Like in atmospheric sciences, it's just a given law because it is true. And anybody that doubts that can look it up. And it's interesting that it doesn't matter where in the world you are, the whole global circuit, because it's connected by these upper conducting layers of the atmosphere, this curve actually applies to the entire world for any given time of day. So it's varying at the same rate across the planet because everything's connected. But it varies by 15%. So if the known measured accelerations of the gravity vary by 0.7%, do you see how that's a problem? If a well-known law in atmospheric science says that it varies by 15% over the course of the day, pretty much debunks his electrostatic theory, just this alone. But it gets better. Actually, the Carnegie study found that different seasons throughout the year, the electric field varies by seasons as well. So this is kind of the first level of evidence here I'm going to go through, but it very much already, we're getting scientific proof that there's no way that the electric field can account for this downward acceleration, because Witsit just wants to use exchange G for A, which is the downward incoherent electrostatic acceleration, and this is showing that electric statics cannot explain this. Okay, so now I just want to look at there's actually a great article, or it's actually not an article, it's from Richard Feynman's Lectures on Physics, and in his electrostatics edition, or his electrodynamics edition, he has a whole chapter on atmospheric electricity, which is just excellent. I recommend everybody take a look at that. And so you can see from this chart here that basically the electric field is going from sea level up into about 50 kilometers, which is about 31 miles, and it's 40,000 volts from the surface up to 31 miles, or 50 kilometers. But the average, Witsit talks about 100 volts per meter as that's some kind of constant going up. Well, it's not. It's only relatively constant for the first 1,200 meters. And that's not very high up. It starts to go down a lot more quickly after that. And up until 50,000 meters or 50 kilometers, it's averaging across the whole scene. The average voltage is 8 volts per meter. But when you get up to 50 kilometers, 31 miles, you're down to now in the millivolts. It's very, very low, and it pretty much drops off to zero. And it's because, first of all, the atmosphere is really thinning out. So this whole capacitor effect, the atmosphere kind of acts like, the dielectric, but the insulator between the two conducting plates. And you can think of the Earth's global spherical electricity as kind of a spherical condenser or capacitor. And it's a leaky capacitor, obviously, because we get lightning strikes about 7 million a day. And we're going to talk about that in a minute. But it's kind of cool to me to really, look at the Earth from a very energetic and electric point of view. And again, this is a book, a really good book. It's a little technical, but by Michael Kelly on the Earth's electric field. But it just helps you to get a greater appreciation for the complexity and just how much this electric field is varying around the world in this global circuit. And the reason why I'm bringing all this up is that we know that gravity falls off much, and I mean, gosh, it's not even comparable. So, for example, when the electric field is about zero at 50 kilometers, guess what the gravitational acceleration is at that level? It's about 9.71. And it's because Newton's law of gravity is a 1 over r squared law. But guess what? R is big R of the entire Earth. So that's so again, to get a 1/4 drop off, you have to be a whole radius of the Earth away from the Earth's surface. So again, this is just why the electrostatics, it just doesn't match reality. We can measure these accelerations. They're very well known. It's not difficult to measure the Earth with an accelerometer or a gravitometer. You can easily measure the acceleration at different altitudes. And they absolutely do not follow at all the level of drop-off that the electric field falls off. I mean, it is just not even close. Like I said, 9.71, what's that? That's just a small, tiny percent drop-off, where with electric field, it's like 100% drop-off at that level. So Witsit, how in the world can this work? I mean, it doesn't work. We know we can measure these accelerations. You cannot describe them with the electric field of the Earth. You just can't. So here I was just bringing this up because he likes to use this, not just Witsit, but Dearth and some other top flat Earth influencers like to do these little electric experiments with balloons and Van der Graaf generators, adding charges, and the aeroelectrodynamic thrust type of little things where they add charge and it's using the negative ion propulsion. But what flat earthers don't get is that with these little propulsion systems, they don't understand what free body diagrams are. So you can have multiple forces acting on an object at the same time. So with Dearth's little balloon experiment, David Weiss, he would add charge and say, look, we can get the balloon, we can get to levitate. This is somehow proof of electrostatics being the cause of gravity. All it is he's not understanding a free body diagram. So what do we got going on there? Well, we got some electrostatics causing repulsion. So that would be on your free body diagram, you have to draw that vector. We have the force of gravity, mg, pulling down, and we have the buoyant force pushing it up. So when we calculate the resultant force of all these forces, then we get the net force, which then creates which direction and with magnitude the acceleration is going to go of the object. So I don't understand. Flat earthers just absolutely do not get the idea of a free body diagram. They think that there's just got to be one force or something. And when they add electrostatics, it's got to just be electrostatics. It's like, no, there's a lot of different forces going on here. So I did see Witsit do the corona motor in one of his video demonstrations. He's something he wants to do, and I don't know how this is. He's going to try to show this as proof that the electrostatics is a source of gravity. It doesn't prove that at all. It just shows that, like I explained, that there is a fair weather electric field, and yes, you can tap into that field and you can create a little bit of electricity on the ground, which is kind of cool, actually. I mean, these corona motors are actually kind of cool, but they don't generate a whole lot of electricity, and certainly they don't in any way remotely prove the electrostatic source of gravity. So this little quote here, I just want to give a source for what I'm saying so that you can see from the atmospheric electricity textbook here, this particular book, it talks about what I'm saying about the average. Well, they put 120 volts per meter, 100 or 120. I mean, it's pretty close. But you can see that at about, in this study, they said at 30 kilometers, the electric field is as low as 300 millivolts. That's pretty much, so you integrate the electric field from the Earth's surface to the ionosphere, gives a result, and then you talk about the electrical potential difference. So it's really, really dropping off to a very, very small level, and whether it's 30 kilometers or 50 kilometers, the point is that when you get up there, it's getting very, very small. So again, gravity doesn't fall off nearly at that level. Okay, so now we get to the big. This is where this is why I use the word catastrophic failure of incoherent dielectric acceleration being the source of the gravitational acceleration, or the source of downward acceleration. So during as I mentioned in the debate, during a thunderstorm, this is a well-known phenomena, and we do have around 7 or 8 million lightning strikes a day. And the electric field, the fair weather electric field, reverses polarity. So again, Witsit and some of these flat earthers that are using this dielectric or incoherent dielectric acceleration idea, which I think came from Ken Wheeler or some guy, I don't know, they got it from someone, that it not only reverses, but it increases by 100-fold or more. So if this is supposed to give a downward, the gravitational acceleration is always down. And as I explained in my video yesterday, it only varies by 0.7% across the planet. Here we have a well-documented phenomena in nature that's showing that not only does it increase by 100-fold, but it switches directions. So if this was true, we would have to be getting alerts on our phones, saying, hey, strap yourself in, the lightning storm is coming, so you don't levitate off. And And I know Witsit, he tried to explain his way out of it, saying that the electrostatic force is weak, but then, like just a minute before, he says it's 10 to the 36 times stronger than gravity. So which is it, Witsit? Is it 10 to the 36 times stronger than gravity, or is it incredibly weak?
When something fluctuates between 9.8 meters per second squared and 9.73, well, okay, because electrostatics is super weak. Well, when you say you try to control for the variable of electrostatics and stuff like that, you can never eliminate it. It's always there. It's 10 to the 36 power stronger than gravity claims to be. How could you find a force much smaller than that?
So absolutely just contradicts himself. So you can't say that it's strong and then you say it's weak when it suits your model, or when you realize that you're in a corner and you can't explain it. Oh, no, it's weak because they just use ad hoc explanations to try to talk themselves out of all these contradictions. It's a failed model. It just can't work. I mean, honestly, what is it? RDD, relative density disequilibrium, which I think some other flat earthers, I mean, that's got less problems than this does. Now, that doesn't work either. But this just has so many more problems than relative density disequilibrium or some of the other theories. Okay, so this is kind of just a cool little map here showing the lightning strikes across the planet. And the point I want to show you here, a couple things. Number one, remember the gravity map I showed you with the very smooth or the very small difference in gravitational acceleration across the planet? Well, this is kind of, in a way, the electrical version of that, or electric field version. And so when you look at these spots where you got a lot of lightning strikes, remember, each lightning strike is not only increasing the potential by 100 to 150 fold, but it's reversing directions. So this is why I kept telling him, even in the first debate where they just weren't getting it, that the electric field varies wildly across the planet, and there's just no way you can use that to describe gravity, which we know is very stable and constant at sea level. And whatever anomalies there are, they're just very, very, very small. I mean, 0.0004, whatever, remember, percent, it's just so much smaller than the gravitational force. So those little anomalies made no difference, where these anomalies are catastrophic. So you can't even call them anomalies. They're just, it is what nature is, but the electric field is a much different, and the electric force is much different than gravity. You can't say the electric force is the same as a gravitational force and then say it's the same as a nuclear force, which actually binds the nucleus together and even holds like charges together, where Coulomb's law says they should repel. So again, their model is just riddled with contradictions when they try to say that electrostatics is everything is electrostatics. So now I kind of want to get into Witsit and his little. He's doing these little review videos like I am of it. Now he says that Newton's gravity is it's a measured, observable fact that we can all agree upon, 9.8 meters per second. So let's kind of, is it though, Witsit? Is it really an agreed upon 9.8 average? Let's take a little look at that, because now at the surface of the Earth, in a way, you could say, okay, we just see that everything falls with an acceleration of 9.8 meters per second squared. And okay, we can just, we have these Newton's laws of motion, and we don't know what this acceleration is due to, and we can just plug it in and kind of make some things work. But what if we're going to try to shoot a satellite into space? Or what if we're going to try to calculate those forces 1,000 miles or 100 miles up in the air, away from the surface of the Earth? Or what if we want to calculate the orbits of the moon around the Earth? Well, now you got a problem. You can't use the agreed upon average, because that only works at sea level. And again, it doesn't tell you at all where it came from, where Newton's laws of gravity do. In fact, like I showed with the Cavendish experiment during my presentation, we can actually calculate G, and we use that to do the Cavendish experiment. We get big G, and we get the mass of the Earth, and now we can plug that in, and we can solve little g at any altitude, which is really cool, actually, because you can use it to calculate the escape velocity, orbits, and what Witsit doesn't seem to understand with his little, F equals ma, that's the only equation he could give me. This is why you can see the little red question mark here. It's like, okay, Witsit, how from your electrostatics model, let's just give him the benefit of the doubt. Okay, let's just say, forget about lightning strikes, forget about the daily variations in electric field, forget about the seasonal variations. Okay, let's just play his game. Okay, let's say it is 100 volts per meter. Okay, so if I have something with a certain amount of charge, say 2 meters above the surface of the Earth, what's going to be the acceleration then? Or, is it charge? Is it mass? How do we combine both charge and mass in your model? because if it is electrostatics, you have to use Coulomb's law. So the electric field, like for example, we would use F equals QE, and Q would be like a test charge you can put in the potential, and you can see what the force is. So, but again, charges and masses aren't the same thing. So now I kind of just want to show you how nonsensical it really gets when you try to combine the two. And again, I kind of did some calculations just last night or yesterday. And you don't have to really follow along with all this, but basically I have two situations. At the top here, you can see gravitational force. So look how nice and clean that is. You just have, force equals mg, objects at the macroscopic level are electrically neutral. And we just use Newton's laws, and they're very accurate to describe in our inertial frame, the motions of objects in our everyday world. But now, the big problem, again, we're playing ball. We're just saying, okay, let's just give them the benefit of the doubt, 100 volts per meter. So if we're using electrostatics now, here's the big problem. There's a couple problems. The first one is, in Newton's laws, because inertial mass equals gravitational mass, they cancel each other out, and that's why you get a constant acceleration no matter how big the mass is. Remember, in the debate I showed big F over big M over little f over little m, because the greater the mass, the greater the gravitational force by the Earth, but the greater the mass, the greater the inertia, or the greater the resistance to motion. So this was Einstein's big insight to creating general relativity, that inertial mass is the same thing as gravitational mass. They cancel out. This is where kind of the curvature of space-time and all that came from, or started from. Now, unfortunately for Witsit and the people using this model, when you actually use electrostatics, you got to set QE equals to MA. So again, you can't just say F equals MA Witsit. That doesn't cut it, because you can only empirically kind of use that as an ad hoc way at sea level. We need an equation from you that'll give us those forces at different heights above sea level. You don't have anything like that. You're just assuming that the acceleration is always constant, and it's not. And you don't even have anything to account for, rotating reference frames and other things like that, based on what we know as Earth's gravity and some of those forces. Because you don't believe in Coriolis, you don't believe in centrifugal. It's all. So it's kind of hard to explain this to flat earthers, because they're just denying reality. And so when you try to say, well, you got to explain this, they're like, well, no, escape velocity. We don't believe in anything above. What did Witsit say during the debate? Anything above 50 miles up, they don't even acknowledge anything above 50 miles. But again, playing his game within 50 miles, 100 volts per meter, you're getting an equation from electrostatics where you have mass in the denominator, meaning that the force due to a charged object is going to be inversely proportional to the mass, meaning you're not going to have a constant acceleration. You can't. But here's the bigger problem. You can see my red, blue, and green line here. Unlike mass, electrical objects can be negative or positive. So in order for this to work, Witsit, on your model, everything has to, because we know the ground's negatively charged, right? So that means everything has to be positively charged. But what does that mean? Well, if everything's positively charged, then won't all objects repel each other? If everything is falling at 9.8 meters per second squared at the surface, that would mean, if you're using electrostatics, that everything has to be positively charged. And we know things. I have a little meter here, a little show and tell here. This is a little electrostatics meter, and I can go around and measure the electric fields of things. In fact, the day of the debate, I didn't really bring it up during the debate so much. I kind of wanted to, but I went around and just tested a bunch of bulk objects, and I just got zeros almost everywhere. However, if I rubbed my socks on carpet, or if I went in the dryer and with static cling, or if I rubbed my balloon on my shirt, then this thing would go off the chart. So again, things you can just prove to yourself with a little. This is $300. It's not cheap, but a little electrostatics meter. This measures electric fields, and in our everyday world, things are not electrostatic, Witsit. Measurably so. Now, what he's trying to do is he's trying to say mass and electrostatics are the same thing, which that's just going to a whole nother level of pseudoscience. But again, you can't just say that, because if you're invoking the fair weather electric field of 100 volts per meter, that has a definite downward electric field, you have to use Coulomb's law. You have to use Coulomb's law. You can't get around that. And, this is just a catastrophic failure of this system, of this model to explain reality. It just doesn't work. So again, you can go online, you can use little calculators with gravitational acceleration by altitude. And again, it's just to show you that how slowly the gravitational acceleration drops by altitude. And that when you get up to 30 kilometers or 50 kilometers, you're still at about 9.7, where the electric field is 0. I mean, how in the world can that work? And if you're using electrostatics to describe downward acceleration, how in the world can how can people be believing this? That's what I don't get. It's like, again, maybe they haven't heard my presentation or someone else say similar things. But if you are kind of on the fence or you are not sure, I mean, this alone is like clear evidence that what they're saying is just a bunch of nonsense. And I want to end this talk today by talking a little bit about a couple things, about why they have to debunk gravity. You say, well, why don't they just accept gravity? Well, Newton's laws of gravity, as we know, are 1 over r squared drop-offs, measurably so. I couldn't get Witsit to admit it during the debate, but had he did admit it, which he should because that's what we can measure, a 1 over r squared law actually comes from spherical symmetry, because the surface area of a sphere is 4 pi r squared. So this 1 over r squared, it comes from a spherical symmetry, so not a flat plane. You can't have gravity and a flat earth. They just don't work. And this little animation at the top shows what happens. So if you had gravity working on a flat earth, the center of mass would be in the middle, right? And people in Australia and the sides towards the ice wall, the gravity would be pulling them sideways. In fact, so much so, if we did live on a disk and gravity was real, if you were at the South Pole, the very edge, it'd be like hanging onto a cliff, right? Because the center of mass would be basically, if you're at the very edge out here, let's say this is the ice wall. Well, this is the edge of the disk. That means the center of mass now is pretty much parallel along this line. So you're basically hanging from a cliff. In the middle, at the North Pole, you would have a relatively downward acceleration. But as you went further and further out, this would mean that trees would be bending sideways and you'd throw a ball and it would go backwards behind you. I mean, just all this nonsense happens when you got a center of mass on a disk. So gravity can't work. And in fact, this is the reason why we don't see flat disks in space, because gravity pulls things from spherical symmetry because all the forces are in equilibrium in a sphere. And it's actually a well-known cosmological principle that if you have enough mass, it always ends up in a sphere. Unless it's spinning, then it can flatten out if it's spinning. But assume that very little spin. But now the thing like asteroids is they don't have this threshold mass, so they might be in kind of weird shapes. But if that mass was big enough, it's spheres everywhere throughout the universe. Thank you so much for watching. I hope you enjoyed this video. Do like and subscribe my channel. I have many more coming, probably about 15 or so debate review type of topics. And there's just a lot of good stuff brought up in the debates. This will be good material for several videos. So thanks again. Have a great night.